If you look at any distant point in the cosmos, you will see the same thing. Everything is moving away from us. The universe is expanding, and that expansion is accelerating. The space between galaxies is stretching out in every direction. To confirm this, we have spent billions of dollars over the last few decades. We've launched the Hubble Space Telescope, built massive sky mapping operations, and pointed advanced spectroscopic instruments at distant supernovae to track exactly how fast everything is pulling apart. All of this observational data confirmed that the expansion is driven by a positive cosmological constant. In physics equations, it's represented by the Greek letter lambda. For nearly a century, scientists have treated lambda as an empirical accident, a random number we had to go outside and measure to verify. A new paper by Ahmad Mostak proposes a different perspective. By starting from first principles, the paper argues that an expanding universe was the only mathematical possibility allowed by the rules of relativity. This suggests that the expansion we observe through our telescopes is actually a direct consequence of the universe's internal logic. In 1917, Einstein's original equations predicted a moving, dynamic universe. He rejected this, preferring a static model where the cosmos sat completely still. To force this stability, he added lambda as a mathematical counterweight to gravity, holding the universe in a precarious balance. 12 years later, Edwin Hubble used massive telescopes to show that galaxies were actually receding. The physical evidence of an expanding universe made Einstein's static model impossible. Einstein quickly retracted the constant. He abandoned lambda in embarrassment, famously labeling it his greatest blunder. The irony is that his original equations were already correct. Lambda was the vital link his theory required, but he discarded it just as its true function was beginning to emerge. Einstein built his theory of relativity on a single foundational rule: the universe must be entirely self-contained. For a universe to be self-contained, its framework must generate its own physics. It cannot rely on an external ruler to measure its size. It cannot have an outside scale, and it cannot wait for instructions arriving from the edge of space to tell it how to behave. When you map out the rules for how space and time interact under this condition, almost everything locks into place. As we see in this equation, there is exactly one mathematical variable left open. That single undetermined number is lambda. Lambda is the built-in mathematical rule that dictates how the geometry of the universe interacts with itself. Because lambda is the only open variable, we can run a simple elimination test. There are only 3 possible states for it: 0, negative, or positive. We will plug each one into Einstein's rule of self-containment to see which universe survives. First, we test universe 1, where lambda equals 0. This creates a flat, static universe. The geometry works, but the framework loses its scale. It has no built-in size until an external ruler measures it. Requiring that outside ruler violates the rule of self-containment. Next, we test universe 2, where lambda is negative. Here, the timeline bends backward into a continuous loop, but this universe has an outer edge. Outside information bleeds in from the boundary. Relying on external instructions means it isn't self-contained. Universe 2 fails. Finally, we test universe 3, where lambda is positive. Time extends infinitely, and the algebra locks in its own shape and scale. It provides its own internal grid without any help from the outside. A moment of wonder. A positive lambda is the only state that passes Einstein's test, and mathematically, a universe with a positive lambda is guaranteed to expand. Every mathematical tool required to prove this was sitting on Einstein's desk by 1915. In his 1917 paper, Einstein explicitly wrote that the universe must be viewed as a self-contained continuum with no outside boundaries. He set the exact right parameters, but when his own equations pointed toward a reality that was moving and expanding, he lost his nerve and forced the math to sit still. The algebraic proof of an expanding, accelerating universe was sitting silently in the equations 83 years before astronomers finally saw it in the sky. Einstein's decision to withdraw the constant stood as his most significant error. By following his own mathematical principles to their end, he would have predicted the expansion of the universe decades before we ever built the telescopes to see it.